Now, dear students, next topic, that is Newton's second law of motion. Now here we have to understand one important physical quantity, that is the linear momentum, or we say momentum. This one is very important physical quantity because momentum is defined as the product of the mass of a body and velocity of the body. And linear momentum or momentum, we say, that is a vector quantity and it is in the direction of velocity of the body. So the product of mass of the body and its velocity, that is called momentum. So we can write momentum P, that is equal to mv. And when we say mass is the scalar quantity, velocity is the vector quantity, so obviously we can understand here the momentum that will be in the direction of velocity. This one is very important physical quantity because here mass is associated with velocity. See, with simple example, you can easily understand the importance of this quantity. Suppose your friend that is on a bicycle and slowly he is moving on the bicycle. Suppose the velocity that is with 5 km per hour. Slow. And now if you pull the bicycle, then easily you can stop bicycle with the force applied by you. Suppose maximum force applied by you, that we consider as a constant force. Now imagine, suppose your daddy is starting car and start motion with speed 5 km per hour. Now apply your maximum force and try to stop it. Is it possible? No, you will be pulled by that particular car in the direction of its motion. So velocity of both the object, bicycle and car, same one. But due to mass of these two bodies, the momentum of these two bodies are different one. Momentum of car, that is large one compared to momentum of bicycle. Therefore, large amount of force is required to stop it. So this one is very important physical quantity. Now momentum is a vector quantity we discussed and it is in the direction of the velocity. Now from this one we can understand the SI unit of the momentum, that is kilogram meter per second. And from that you can write the dimensional formula, that is m1 l1 t minus 1. Okay. Now experiments shows this thing. If same amount of force is applied to different objects for the same time, then change in momentum for different bodies will be same one. And from these observations, this type of experiments, Newton suggested second law of motion. Now Newton's second law of motion suggests this thing: the rate of change of momentum, that is directly proportional to the applied force to it and is in the direction of the applied force. Okay, so rate of change of momentum of the body is directly proportional to the applied force and takes place in the direction of force. So we can write F proportional to delta P by delta T. Here we introduce the proportionality constant K, but this constant of proportionality that we choose k that is equal to 1. So simply we can write Newton's second law of motion, F that is equal to delta P by delta T. Now suppose here we take limit delta T tends to 0. Then we can write F that is equal to limit delta T tends to 0 delta P by delta T. But this can be represented as differentiation. So we can write F that is equal to dP by dt. Okay. Now we know this thing, momentum P that is equal to mv. So in this equation, if we replace P by mv, now mass is constant one. So take it outside the differentiation. So we can write mass into dV by dt. dV by dt, the differentiation of velocity with respect to time t. That is the acceleration. So we can write F equal to ma. So here second law of motion, that is F equal to dP by dt, that is equal to ma. Right? So this one is another form of second law of motion. Now here in component form we can write the second law of motion like this: Fx equal to dpx by dt, that is equal to max. Means the differentiation of x component of linear momentum with respect to time t will give you x component of the force, and that is equal to mass into x component of acceleration. Similarly, Fy equal to dpy by dt, that is may. Similarly, we can write Fz equal to dpz by dt, that is equal to maz. Now, see here, from F equal to ma, we can write the unit of force, that is kilogram for acceleration, that is meter per second square, and this kilogram meter per second square, that is called Newton. So 1 Newton force, that is equal to 1 kilogram meter per second square force. And here we can give the definition of 1 Newton force, or in other words we can say the definition of 1 kilogram meter per second square force. The force which produces 1 meter per second square acceleration in the object having mass equal to 1 kilogram, that force is called 1 kilogram meter per second square force, or we can say that particular force is called 1 Newton force. And from this unit we can write its dimensional formula also, and that is m1 L1 T minus 2. In CGS we can write the unit, that is gram centimeter per second square, and this CGS unit, gram centimeter per second square, that is called dyne. And the relationship between Newton and dyne, that is like this: 1 Newton, that is 10 raised to 5 dyne. Right? Now here we have to think about 2 important points related to this second law of motion. See here, first thing, suppose the force F, that is equal to 0. If F equal to 0, then ma, that is equal to 0. Mass is not equal to 0, means acceleration equal to 0. So here we can say, if the force is not acting on the body, some net force is not acting on the body, then its acceleration will be 0. If acceleration is 0, it implies that we can think about 2 states of motion. Either the body is stationary or the body is moving with constant velocity. So this one is consistent with first law of motion. Clear? And Newton's second law of motion, that is vector law, because here force, momentum, acceleration, all the vector quantities are appearing in this law. Clear?